Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 29th, 2026, about 5 days ago. It reveals that filtering specific tokens during pre-training can lead to a massive 7,000 times effective compute slowdown on undesired capabilities compared to an unfiltered baseline. The paper is titled, Shaping Capabilities with Token-Level Data Filtering. And as we'll see later, this method proves significantly more robust against adversarial attacks than existing safety techniques. Figure 1 illustrates this scaling effect directly. The vertical axis tracks compute slowdown, which essentially measures how much harder it is for the model to learn a concept when data is filtered. On the left, looking at the medical forget domain, the top purple line represents token removal, and it rises steeply as compute scales, reaching that 7,000 times factor. In contrast, the right panel shows that the cost to retained biology knowledge stays much lower, meaning the method surgically removes the hazard without breaking the model. So, having seen the results, Figure 2 breaks down the two specific techniques used to achieve them. The top panel illustrates loss masking. In this approach, the sensitive words, shown here in red, like vaccines or infectious, remain in the input text, so the model retains the context. However, the crossed out arrows show that the training loss is zeroed out for these tokens, meaning the model reads them, but does not update its weights based on them. The bottom panel depicts removal, which is the more aggressive strategy. Here, the hazardous tokens are physically replaced by a special hidden token, effectively scrubbing the information entirely. Okay, having defined the mechanisms, Figure 4 demonstrates their performance as we scale up. These plots track medical loss on the vertical axis against retained capabilities on the horizontal one. Here, we actually want high loss vertically to ensure forgetting, but low loss horizontally so the model stays useful. The arrows indicate that the top left corner is the ideal zone. Notice how the purple line for token removal consistently hugs that frontier, outperforming the green document filtering curve and widening the gap from the beige baseline as models grow larger. Well, while loss curves are informative, Figure 5 checks actual performance on multiple choice questions. The left panel tracks the forget domain, covering exams like Med MCQA and USMLE. Notice how the beige baseline performs well, but the filtering methods drop accuracy drastically, effectively hitting the black horizontal line that represents random guessing. In contrast, the right panel tracks the retained domain. Here, performance on general STEM and non-STEM tasks remains steady, confirming that the model preserves its general intelligence even while surgically removing the targeted medical knowledge. So, while Figure 5 tested static performance, Figure 7 evaluates robustness against an active adversary trying to fine-tune the model. The vertical axis plots the cost to break the safety measures, specifically the number of tokens required to recover the forbidden knowledge. Notice that as compute scales on the horizontal axis, the purple line for token removal remains the highest. This confirms it creates the toughest barrier for attackers, while the pink line for the RMU unlearning method collapses to the bottom, offering the least resistance. Alright, moving from robustness to control, Figure 9 investigates whether these filtered models can actually learn to refuse dangerous prompts without breaking on safe ones. On the left side, for the benign alpaca dataset, we ideally want 0 refusals. Notice how the green bar for document filtering spikes to over 10%, showing that it degrades general utility by refusing harmless questions. Conversely, on the right side for the hazardous health search QA dataset, the purple bar for token removal dominates. It reaches nearly 50%, which is double the baseline, proving that this method makes the model significantly more responsive to safety alignment. Well, effective filtering relies on accurately spotting the right tokens, and Table 1 compares the models used for this detection. The first row shows that a standard modern BERT large model achieves a test F1 score of about 0.81. However, the rows below show that training a custom bidirectional language model, or BILM, and upsampling medical data improves accuracy significantly. The final row highlights the best performer, a 224 million parameter model that reaches nearly 0.9 F1. This confirms that for filtering, a small, specialized detector actually beats a massive, general-purpose one. Wrapping up, 2 takeaways stand out. First, token-level filtering provides a robust defense in depth by stopping models from learning hazardous concepts to begin with. Second, this approach scales effectively, proving that curating the input data is potentially more reliable than patching the model after training. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.